Rectilinear motion, velocity and acceleration. Velocity. Imagine a particle moving along a straight line path in some way. Let t be a variable representing the time elapsed since some reference time when t is equal to 0. And let s of t be the position of the particle at time t measured relative to some reference point where s equals 0. Average velocity over a time interval where t is greater than or equal to a, less than or equal to b, is defined to be the change in position divided by the change in time. Average velocity equals delta s over delta t equals s of b minus s of a over b minus a, or the position at time b minus the position at time a over b minus a. Instantaneous velocity at time t is defined to be the limit of the average velocities over intervals t to t plus h as h goes to 0. Thus velocity is the derivative of position. Velocity v of t equals s prime of t is the limit as h goes to 0 of s of t plus h minus s of t divided by h. Example. Suppose we have a position function s of t equal to t minus 2 cubed minus 2t plus 8. Here's the graph of that position function. The velocity v of t is s prime of t, and that's 3 times t minus 2 squared minus 2. And here's the graph of the velocity. Notice that the velocity is negative when the graph of the position function has a negative slope. Now let's look at an animation of the motion that corresponds to this position function. Now let's look at this again and be sure to notice the direction that the ball is moving corresponds to whether the graph of the position function has a positive or a negative slope. Another example. Suppose we have the position function s of t equals sine of t. Here's the graph of sine of t over the interval from 0 to 2 pi. The velocity then, v of t equals s prime of t equals cosine of t. Now let's look at an animation that corresponds to this position function. Notice that the object here is simply oscillating back and forth between -1 and 1. This, in fact, is what's called simple harmonic motion. Acceleration. Just as velocity is the rate of change in position per unit time, acceleration is the rate of change of velocity per unit time. Thus, acceleration is the derivative of the derivative, or the second derivative, of position. So we have velocity v of t equal to s prime of t, and now we have acceleration a of t equal to v prime of t, or s double prime of t. In Leibniz notation, we can write a of t equals dv dt, which is the derivative with respect to t of ds dt, or the second derivative of s with respect to t. Newton's second law relates acceleration, mass, and force. It says that total force is equal to mass times acceleration. So whenever there's acceleration, there's force, and vice versa. Example. Let's consider the same position function that we encountered in a previous example. t minus 2 cubed minus 2t plus 8, whose graph is shown here. Velocity is just the derivative of position, 3 times t minus 2 squared minus 2. And so the acceleration, a of t, equals 6 times t minus 2, which is just a linear function. Notice that the acceleration is negative for t between 0 and 2, and positive for t greater than 2. Also notice that negative acceleration corresponds to decreasing velocity, positive acceleration corresponds to increasing velocity. Now let's look again at the animation. We'll stop this animation at the point where the acceleration is 0. Notice that over that time interval, from t equals 0 to t equals 2, the object starts out moving forward and is behaving as if there is a force pulling it in the negative direction, which eventually causes it to change direction. Let's watch that again. Now at t equals 2, the acceleration changes sign and becomes positive, and so the object now behaves as if there's a force pulling it in the positive direction. Notice that it does continue to move in the negative direction for a moment before turning around and going in the positive direction. So now let's look at the entire animation one more time. Forward, backward, forward again. Free fall near the Earth's surface. Let h of t be the height of an object in free fall near the surface of the Earth. The gravitational force on the object, and thus its acceleration, will be roughly constant. This acceleration due to gravity is minus g, where the value of g is roughly 32 feet per second squared, or about 9.8 meters per second squared. If we assume air resistance is negligible, or if the fall is occurring in a vacuum, then h of t is the following quadratic function. H of t equals minus 1/2 g times t squared plus v naught t plus h naught. Now, let's notice that h naught has a particular meaning here. It is exactly the value of h at t equal to 0, or in other words, the initial height of the object. So now let's look at the velocity and the acceleration. The velocity is linear. V of t equals minus gt plus v0. Now let's notice that v0 is precisely the value of the velocity at time 0, or the initial velocity. And finally, the acceleration is the constant minus g. So constant acceleration corresponds to linear velocity, which corresponds to a quadratic height function. Example. Let's suppose that a ball is dropped from a height of 100 meters. That means that our initial height, h naught, is 100. The fact that the ball is dropped means that the initial velocity is 0. There would be a non-zero initial velocity if the ball were thrown upward or downward. Also, since our distance units are meters, we'll use 9.8 as the value of g. So, our height function, minus 1/2 gt squared plus v0 t plus h naught, takes the form of minus 4.9, which is 9.8 divided by 2, times t squared plus the initial height, 100. So our velocity, v of t, is minus 9.8 t. Here's the graph of the height function over the time interval when the height is greater than or equal to 0. In other words, up to the time when the ball hits the ground. Here's the graph of the velocity function, minus 9.8 t. Notice that the velocity is always negative, corresponding to the fact that the ball is always falling. Let's look at a little animation that traces the graph as the ball falls. Now again, notice that our initial velocity is 0, so the slope of the height function is 0 at time 0. Then as the ball falls, it gradually picks up speed. Actually, its velocity is decreasing until the ball hits the ground. So when exactly does the ball hit the ground? Well, we'd like to know when h of t is equal to 0, and that happens when 4.9 t squared equals 100. Or t equals the square root of 100 divided by 4.9, which turns out to be very close to 4.5 seconds. So this tells us that our height function, h of t, is valid only for t greater than or equal to 0 and less than or equal to that 4.5. This is the natural domain for the height function in this situation. Example: a ball is thrown straight up from a height of 6 feet with initial velocity 64 feet per second. How high does the ball go? We first write the height function. H of t equals minus 1/2 g t squared plus v naught t plus h naught. Now, since our units of height are feet, we'll use g equals 32 feet per second squared. So the first term is minus 16 t squared. The initial velocity is 64 feet per second, so our second term is plus 64t. Our initial height is 6 feet, so that's h naught, and so we have h of t equals minus 16t squared plus 64t plus 6. Now let's find the velocity function. To do that, we take the derivative of the height function and get minus 32t plus 64. Notice we can factor minus 32 and write this as minus 32 times t minus 2. Now when the ball is at its highest point, the velocity will be 0. So we'd like to know what the height is when the velocity is 0. So let's find out when the velocity is 0. V of t is equal to 0 when t is equal to 2. So now we compute the height at the time when the velocity is 0 and conclude that the maximum height is h of 2, which turns out to be 70 feet. Now let's look at an animation of the flight of the ball. Notice the ball goes up, reaches its maximum height when the velocity is 0, then begins to fall and eventually hits the ground. Example: let's show that for all t while an object is in free fall, its height and its velocity satisfy 2g times h of t plus v of t squared equals 2g h naught plus v naught squared. Notice that this says that the quantity 2g h of t plus v of t squared is constant. So let's take our height function h of t equals minus 1/2 g t squared plus v naught t plus h naught, and our velocity function minus gt plus v naught, and substitute those formulas into 2g h of t plus v of t squared. So we multiply the height function by 2g, getting minus g squared t squared plus 2g v naught t plus 2g h naught, and we add the square of the velocity. Next we expand that product into g squared t squared minus 2g v naught t plus v naught squared. Now, notice that we have minus g squared t squared plus g squared t squared, as well as 2g v naught t minus 2g v naught t. So the remaining terms give us 2g h naught plus v naught squared, which is exactly what we wanted. Remark: if we multiply both sides of this equation by 1/2 times the mass of the object, we have the following equation. The first term here, mgh of t, is potential energy. The second term, 1/2 mv of t squared, is kinetic energy. So this says that the sum of the object's potential and kinetic energy is constant, and in particular equals its value at time 0 at all times. This is conservation of energy. Let's look at a different approach to this problem. Let's take the quantity 2gh of t plus v of t squared and take its derivative with respect to t. The derivative of 2gh of t is just 2gh prime of t, and the derivative of v of t squared using the chain rule is 2 times v of t times v prime of t. Now, h prime of t is v of t, and v prime of t is a of t. And a of t is just the constant minus g, and so therefore this derivative with respect to t is equal to 0. Now this tells us that the quantity 2gh of t plus v of t squared is constant. That constant value must be the same as its value at time 0, so we have the desired equation. From the formula in the previous example, we can easily derive formulas for maximum height and impact velocity. Since h of t equals its maximum value, let's call it h max, when v of t is equal to 0, we can substitute those values into the equation to obtain 2gh max plus 0 equals 2gh naught plus v naught squared. So now we divide by 2g and obtain the formula h max equals h naught plus 1 over 2g times v naught squared. Let v final be the velocity v of t at the instant when h of t equals 0. That is, v final is the velocity when the ball hits the ground. Then, substituting h of t equals 0 and v of t equals v fin into our equation, we find that 0 plus v final squared equals 2g times h naught plus v naught squared, or v final equals minus the square root of 2g h naught plus v naught squared. Notice that we take the negative solution there because we know that the ball is falling when it hits the ground. Bounce. In all of the examples we've seen so far, we only considered motion up until the time when the object hits the ground. Now let's look at an animation of a ball that's being dropped from a tall building. Imagine this is a basketball that's being dropped from the top of a building. Begins to fall, hits the ground and bounces, hits the ground again, hits the ground again, and so on. This is the graph of the height function for the animation we just watched. Now let's watch the animation again and notice how the graph is drawn as the ball falls and then bounces 3 times. So what's happening here when the ball bounces? Let's look at the first bounce. When the ball hits the ground the first time, it does so with a velocity of about negative 44 meters per second. The assumption that was made here is that the initial velocity for the part of the height function between the first and second bounces is half of the absolute value of the velocity with which the ball hit the ground. So our initial velocity for the part of the height function between the first and second bounces is about 22 meters per second. Now, the ball hits the ground later, it turns out, with a velocity of about negative 22 meters per second. So the initial velocity for the part of the height function between the second and third bounces will be about 11 meters per second. And so on at each of the subsequent bounces. Now, a better way to think of this from a physical point of view is as follows. Kinetic energy is 1/2 times mass times velocity squared. So if the absolute value of the velocity is cut in half at each bounce, that means that the kinetic energy is being reduced by a factor of 1/4. So each time the ball bounces, it loses 3/4 of its kinetic energy. Also, the 1/2 coefficient here is nothing special. In general, that would be some number between 0 and 1. For something like a super ball or a golf ball, it would be closer to 1, and for, say, a basketball that was low on air, it would be closer to 0. Now here's the graph of that height function again, along with the graph of the velocity. Notice that the velocity has a discontinuity each time the ball bounces. Also notice that a maximum height is attained between each bounce at a time when velocity is 0. Now again, the ball hit the ground the first time with a velocity of negative 44 meters per second, and then reverse direction with an initial velocity of positive 22 meters per second. Then it hit the ground again with a velocity of negative 22 meters per second. It reversed direction and went up with an initial velocity of 11 meters per second, and so on. Now the first part of the height function, that is between time 0 and the first bounce, is minus 4.9 t squared plus 100. From that we solve for the time of the first bounce. We'll call that t1, and it's approximately 4.52. Using that, the second part of the height function is minus 4.9 times t minus t1 squared plus the new initial velocity of 22 times t minus t1. Using that formula, we can solve for t2, which turns out to be about 9.01 seconds. And then the third part of the height function is minus 4.9 times t minus t2 squared plus the new initial velocity 11 times t minus t2. Using that, we solve for t3 and then construct the fourth part of the height function in a similar fashion.